So I have posted your homework number 4 for you, and that will be, probably we will finish that material today, and then move into homework number 5 next week. The homework number 4 includes these 3 forces right here. And then we will do more applications of these 3 and introduce friction to make up homework number 5. And after homework 5 is done, that will be the cutoff for exam 1. So I'm anticipating announcing exam 1 next week, giving you the official 2-week heads up. Okay, any quick questions, administrative or logistical, before we get started? Okay, so here's our 3 forces so far. We have rules of thumb for them so that we can fill them in ourselves on problems. Force of gravity, as yet, remains a mystery. Its size is mg, which is basically our cop-out in saying that whatever this force is, it always causes a particular acceleration to objects. How exactly it does that is still as yet undetermined, but the force is always downward. The tension, include that in a problem if there's a rope or a string attached to your object. Its size varies, but it is always along the rope away from the object. It always pulls, never pushes. And then finally, we haven't even done anything with it yet, but introduced it at the end of last time, the normal force. That's the support force from a solid surface. So don't include it if your problem does not have a solid surface touching your object. Its size varies, but it varies very much with a purpose. It varies as needed to prevent smushage. So if you can't read that word, that's smushage, okay? So this force is what protects the structural integrity of the surface. So if you have 1 or 2 or 17 forces that are threatening to take the object into the forbidden zone where there's a solid surface, the normal force makes sure that doesn't happen. It exerts a force perpendicular to away from the surface as to make sure you don't go in there, okay? So with that in mind, I want to do an example problem where we get a chance to try out normal force. This is our first, but by no means our last encounter with the inclined plane. Question?
This might be redundant, but if it's on the ground, the normal force is for something like a table. It's not.
You can ground anything. The ground, if it's something sitting on the ground too. Yes.
Okay.
Yep. Any solid surface that you don't want your object to, be like a ghost and go through it. We know that doesn't happen in real life. So any solid surface where the object can't go into it.
Okay.
It can include your hand. It can include any solid surface. That's what it's for. So this is our inclined plane problem. I'm going to take my 6-step recipe. My force problem-solving strategy has 6 steps. I'm going to take you through it. I'm going to show you that it works. Along the way, if we stick to the recipe very carefully, we'll find some interesting twists and turns. I'm also going to do this symbolically, so we get a chance to do a fully symbolic solution. And I'm going to show you one of the advantages of symbolic solutions, which is you have a method of error checking called checking your limits to just kind of try out and make sure your answer is correct. Okay? All right, so let's get started. Inclined plane, what is it? It's a tilted surface. So we've, of course, been dealing mostly with horizontal surfaces, flat surfaces, or, of course, when we're moving vertically under gravity only. But of course, there are tilted surfaces in the world. We should be able to analyze that too. The tilt we usually characterizes an angle theta from the horizontal. So that's one of the givens. Again, there is going to be no number that I'm going to give you for that. I'm instead just going to give you that variable with the understanding that that variable is allowed in the answer. I'm going to have a mass m that I put on that. So we're going to solve the solution not just for 1 kilograms or 2 kilograms, but any mass, a general mass m solution. One of the things that we have not yet gotten to is friction, so this is going to be a frictionless inclined plane. You have to imagine a perfectly smooth surface. It's not rough at all, okay? So, what are my questions that I'm going to ask? My questions I'm going to ask is, what is the size of the normal force? And what is the acceleration, or size of the acceleration, that the object will experience? So, let's go through the recipe. Step 1, identify the object of interest. Pretty obvious here, it's the mass on the incline. Okay, step 1 is done. Step 2, identify forces on it. So we go to our list, and we see which force would be appropriate. Should we include the force of gravity? Does the force of gravity pull on this thing? Yes. It pulls straight downward. So let's put that in. See if I can find a different color. Force of gravity is straight down. Gravity doesn't care that your surface is tilted, okay? For instance, if you're walking up a steep hill in San Francisco, downtown somewhere, okay? If you decide to jump up and down, you will go like this, right? Not like this, okay? Force of gravity is not that way, okay? It's still straight down, okay? All right, how about tension? Should we include a tension? No, there's no rope, so don't include a tension just because you know about the force of tension. Don't try to shoehorn it into a problem just because you know about it. Do we include the normal force? Yes, we do, because if that force of gravity were going to do its thing, the thing would go straight down, and there is a surface there. So we go ahead and we put it in. However, that force acts perpendicularly to the surface. So now we see that those two forces do not act along the same line. So there is going to have to be some SOHCAHTOA involved a little bit later. Okay? But for now, we're done with step 2. Step 2, we are identifying the environmental influences on our object. We have 2. So, step 3, you have it written down from last time, so I didn't write it down again. Step 3, choose some axes. So, don't just always choose the quote-unquote standard axes. Give this some thought. And in this problem, it's going to lead us to a little bit of a strange choice. If your acceleration is 0, or you don't know the direction of the acceleration, then you want to minimize your components. You can pick whatever you want. But if the direction of the acceleration is known, you want to pick one of your axes along that. We know that in this problem. This thing is going to slide downhill. So we pick x is downhill and y is perpendicular to that, so perpendicular to the surface as well. So we're going to break these forces up into parallel and perpendicular to the surface. Now again, why do we want to do this? Well, this narrows it down. All of my acceleration is x. All of my acceleration is along the surface. My y acceleration is 0. So I've cleverly chosen my axes so that I can automatically say that all the acceleration is on one axis and none of it is along the other. So how do I know the y acceleration is 0? Well, we have to contemplate, can this thing go in the negative y direction? No, because there's a surface there. Is it going to jump up off the surface in the positive y direction? No. Okay, there's going to be no motion perpendicular to the surface. It's all parallel to the surface. Okay? So this ultimately makes our lives easier to know that one of the components is 0 right off the bat. And when we search for the total acceleration size, we're really searching for one component, because the other component, by a judicious choice of axes, is not even there. It's 0. All right, so that is step 3. We move on to step 4. Now that we've chosen our axes, we break up the forces into components along those axes. So alongside, I might draw a free body diagram. And one of the things that I don't have to break into components is the normal force, because the normal force is entirely in the y direction. So all I have to really do for that is to recognize it's a positive y component. And remember how I do this? The size is, the directions on the outside, it's plus y, and then the size is on the inside. You don't want a nasty negative surprise coming out of the inside of the parentheses. The things inside the parentheses are just the size, just a number. The plus and minuses are going to be on the outside. So then we turn to the force of gravity. This is the first time where the force of gravity has been diagonal relative to the axes that we are choosing. Okay? So you notice here, the force of gravity, it's not plus x only, it's not minus y only, it actually has components, so we need to break that up. So one of the things, especially when you're first getting started, you might want to rotate into the standard view. So draw your axes like that, but then realize that your force of gravity looks like this. Okay? So the angle between your x-axis and the force of gravity is less than 90 degrees. So this right here, it's a minus y component and a positive x component. Be really careful when you're doing this. Make sure that the entire force is the hypotenuse. Okay? If you draw some weird looking triangle where the entire force is not the hypotenuse, you've done something wrong. Okay? So I see this all the time. Students do this. They draw their components in like this. You've just drawn that one of the pieces or components is the longest side. How can a piece be bigger than the whole thing? So if you draw it onto this graph, it should look like this. So the two legs of the triangle are the two components, and the entire force is the hypotenuse, the whole thing. All right. So let's go ahead and do it. First of all, this size is hypotenuse is mg. Now it's really good that g isn't negative, because the hypotenuse is never negative. That doesn't even make any sense. Plus and minus is for components. Plus and minus is not for the hypotenuse as a whole. Okay. Now, in order to break this triangle up, we need to find this angle. So let me do a brief bit of side geometry. You don't have to do this every single time. I'm going to do it for you once, so you never have to do it again. Here's a bit of side geometry. I guess I'll do it over here, just to have it away from the main flow. Here's the force of gravity. Oh, and let me draw the mass as a point particle so I don't have to worry about the shape of it confusing me. The shape is irrelevant. If this angle is theta, and this is a 90-degree angle, because of course the force of gravity goes straight down through the base, what's this angle here? 180 minus 90 minus theta, or 90 minus theta, right? So among the many geometric things that we will never need in physics, one of the things that you do need to know is the sum of the interior angles of a triangle is 180. And of course, since this happens to be a right triangle, one of those angles is already hogging 90 of it, and so the other two have to add up to 90. As we say, they are complementary, right? The two other angles have to add up to 90. So if one is theta, the other one's 90 minus that. All right. Now I go ahead and put back in the components, which look like this. Remember, the components are broken up perpendicular and parallel to the surface. And so the angle here, what is that angle?
Theta.
It's just theta again, right? So these two angles right here have to add up to 90 as well. And So the complement of a complement is back to the same angle. What we've just done, do it once so we never have to do it again. The angle that we are going to use for our SOHCAHTOA here is actually the same as the angle of the incline, which is great because we can't just make up our own angle and include it in the answer. We were given the angle of the incline. And so it's nice that we can use that very same angle for our SOHCAHTOA. All right, so we can do it over here if it's more comfortable. Which side is this? Is this adjacent or the opposite? Adjacent, so which gets cosine or sine?
Cosine.
Cosine. So it's, and is it positive or minus y component? Minus. So it's minus, and the size of it is hypotenuse times cosine of theta. That's the y component. That's how much of the force of gravity acts directly into the surface. Okay, how about this component? This is the x component. Is that plus or minus x?
Plus.
Plus. It points along the plus x-axis. It is also the opposite side, so it's hypotenuse times sine. So what we have one component that's minus. We have the other component that is positive. The hypotenuse is nothing, right? You can't use plus and minus for the hypotenuse. You can really see now why we choose G to be positive, because here there's one negative component, one positive component, and what we look to G for is just to help us provide the amount. We've already decided that we have one component of each sign. So again, remember, G is not negative. G is just the amount, and then we decide ourselves what we should assign. And here we have to assign not one but two components, one of which is minus and one of which is plus. Okay? So we can put them back over here in the original diagram, minus mg cos theta over here, plus mg sine theta over here. And we can also copy them both into the free body diagram, because as I like to do in my free body diagrams, I only include forces that are already broken up. That way I can analyze the x and y directions independently. So that's what we have. That's our free body diagram. It's on a diagonal because remember we used diagonal axes. X is a proxy for the parallel to the surface, and y is a proxy for perpendicular to the surface. If you draw a good free body diagram, you pretty much can already see what's going to come out of the equations. Here's what's going to happen, just to give you a little bit of a give away the punchline. We already said there should be no y acceleration, which means the y components have to kill each other. So basically you have the force of gravity. We split it up into two components, and one of those components, this one, the mg cos theta, is trying to accelerate the object into the surface, and the normal force says, sorry, you can't come in here. So the normal force's job is to kill the offending component. But the normal force does not have a problem with the other component of gravity, because the other component of gravity is just going to make it move parallel to the surface. And that's perfectly fine. So we're thinking of the force of gravity in two pieces. One piece tries to go into the surface, one piece tries to bring it parallel. Normal force puts a stop to the first one and is perfectly fine with the second one. Okay? So basically what we have here, in a nutshell, is that the normal force will cancel off just a part of the force of gravity, and the other part is left over, and that is what causes the acceleration. Okay? So in a nutshell, the normal force cancels one part of the force of gravity, and the other is left over to cause a net force and, of course, any resulting acceleration that comes with it. That is conceptually what is happening here. Okay? So we've pretty much already telegraphed the results, but let's continue on with our problem-solving strategy. So we did steps 1 through 4 now. Step 5 is to plug it into the equations. So here's the x equation, and here's the y equation. The essence of Newton's second law is that you can have a bunch of forces acting in a given direction. If there's anything left over after they are all possibly acting in different directions, if there's a net force left over, it will lead to acceleration. If there's no net force left over, you won't have an acceleration. So let's start with the x direction. We only have one thing. There's no competition whatsoever. There's only one thing on the list, and that is the component of gravity that acts parallel to the surface. And that leads to, for sure, we will have some acceleration. Because if it's, there's no tug of war here, it's completely uncontested in the x direction. You have one thing, and that one net thing will be the net force that will lead to the acceleration. In fact, we can cancel off and find the acceleration right here. The acceleration is plus g sine theta. Now, if you're a stickler, you might point out, isn't that just one component? Yes, except for, remember, we already set it up, so the other component was 0. We'll go ahead and throw that in while we're at it. So if you had to reassemble these two into a magnitude, you don't have to use Pythagorean theorem and inverse tangent for that, although it would work. You can just look and see all of it's in the x, none of it's in the y. What's the magnitude of the whole acceleration? It's g sine theta. And that, of course, is one of the things that we were asked for. We were asked for the size of the acceleration overall. And it does play by the rules, because only thing in that expression is theta, which we were given, so that's allowed in the answer, and g, which is a known constant, which is always allowed. Okay? So remember, we're going to have two equations here, so we can solve for up to two unknowns. Sometimes they're intertwined, and we have to do some algebra to isolate them. But in this case, what's going to happen is one of the things we want pops out of one equation, and the other thing we want pops out of the other. We get lucky that they both just come out with what we want. So let's go ahead and do it in the y direction. Now we have some competition. We have two things. And of course, by design, the normal force has to cancel that component of gravity by being the same size. And that's the other thing we wanted, right? And that just pops out of there. All the things that are in the answer are allowed. M and theta were given, and g is always allowed. Let me ask you this. Is this normal force, is this bigger or smaller than mg? The force of gravity. Is this mg cosine theta, is that bigger or smaller than mg itself? Smaller. Because remember, the surface did not have to cancel off the entire force of gravity. It had to cancel off one part of it. And a part is smaller than the whole. The force of gravity here came with two components, one of which was directly into the surface, and the other one was parallel to it, so the surface didn't care about that. So if you're going to cancel one piece of the force of gravity, you let the other piece do its thing. Now the normal force is smaller than the force of gravity as a whole. Okay? So that's our second result. And we're nominally done with the problem. I'm going to talk through the characteristics of the answer, however, and along the way show you a way to error check called checking your limits. Are there any quick questions before I proceed onward to that? Okay. So I hope to show you how these two answers make sense by doing a process called checking your limits. This is a skill that is very, very useful to have in your back pocket. Here's what this is. It's a method of error checking symbolic solutions. But the solutions have to be symbolic. They have to be generic. They have to claim to solve this problem for a wide range of different parameters, because that is how we're going to leverage checking that they make sense. Because here's the thing.